Imagine wearing a watch, where time is shown using glowing LEDs. Instead of numbers, no digits, no clock hands, just binary. And someone asks you, if exactly 3 LEDs are on, what time could it be? Sounds simple, until you realize there are 720 possible times in a day. Today, we're solving LeetCode 401 binary watch. And by the end, you'll understand how bit counting can turn brute force into elegance. We're given turned on the number of LEDs currently glowing. A binary watch has, for LEDs for hours values 0 to 11, 6 LEDs for minutes values 0 to 59. Each LED represents a bit, 0 or 1. The rightmost LED is the least significant bit. Our job? Return all valid times where the total number of on LEDs equals turned on. In other words, we're counting bits to generate every possible combination that forms a real clock time. Bit counting turns what seems like brute force into elegant logic. Rules: hours, 0 to 11. Minutes, 0 to 59. No leading 0 in hours. For example, 1 o'clock should be 1 o'clock. Minutes must always be 2 digits. For example, 10:2 should be 10:02. Let's try. Turned on equals 1. That means only one LED is glowing. So either 1 LED in the hour or 1 LED in the minute. Every combination that follows these rules forms a valid binary watch time. Hours with 1 bit on. Binary possibilities: 00011, 00102, 0104, 1008. So we get 1 o'clock, 2 o'clock, 4 o'clock, 8 o'clock. Minutes with 1 bit on. Binary possibilities: 0000011, 0000102, 0001004, 0010008, 0100016, 100,032. So we get 001, 002, 004, 008, 016, 032. Combine everything: 0:01, 0:02, 0:04, 0:08, 0:16, 0:32, 1:00, 2:00, 4:00, 8:00. Boom. That matches the example. Aha moment. We're not flipping bits. We're counting how many bits are 1. Here's the trick. Instead of generating binary combinations manually, we just try every possible valid time. How many are there? 12 hours, 60 minutes. 12 times 60 is equal to 720 combinations. That's tiny. We can literally check all of them. For every hour, 0 to 11. For every minute, 0 to 59. If hour.bit_count plus minute.bit_count equals turned on, then it's valid. Why bit_count? Works. Bit_count tells us how many ones are in the binary representation. Example: 5101 bit_count equals 2. So we don't manually count bits. Python does it for us. Here's the Python solution. We define a class solution with a method readBinaryWatch. Taking turned on as input, we start with an empty list called result. For every hour from 0 to 11, and for every minute from 0 to 59, we count total LEDs on. If hour.bit_count plus minute.bit_count equals turned on, it's a valid time. We append it to the result. Formatting minutes to always have 2 digits. Hour, minute. 0 to D. Finally, we return result, which contains all valid binary watch times for the given turned on LEDs. We start with result equals. It stores all valid times. For hour in range 12. We only consider valid hours, 0 to 11. For minute in range 60. We only consider valid minutes, 0 to 59. Hour.bit_count plus minute.bit_count. This is the magic. Count how many LEDs are on in the hour. Count how many LEDs are on in the minute. Add them together. If the total equals turned on, we add it to result. F, the hour, minute. 02D. An important formatting detail. Minute, 02D ensures 2 digits. It adds a leading 0 if needed. Example, 505. This satisfies the problem constraint for binary watch output. Time complexity, 12 by 60 equals 1. Because we always check 720 combinations. Space complexity depends on the number of valid outputs. This is technically brute force, but perfectly optimal because the input space is tiny. Common mistakes to avoid. Generating binary combinations manually. Forgetting minute formatting. Allowing hours greater than or equal to 12. Not understanding bit_count. Keep these in mind, and the binary watch problem becomes simple and elegant. This problem tests several key skills. Understanding of binary representation. Basics of bit manipulation. Smart brute force thinking. And formatting discipline. Interviewers love when candidates use built-in tools like bit_count efficiently. It shows you understand both the problem and the language. If you're enjoying these clean breakdowns, hit like and subscribe. I post LeetCode explanations that actually make sense. Now I want to challenge you. What happens if turned on equals 9? Think about it. Maximum LEDs possible. Hour max bits equals 3. Since 11 in binary is 1011. Minute max bits equals 6. So max total equals 9. But does any valid time actually use 9 LEDs? Drop your reasoning in the comments. Let's recap. We didn't generate binary strings. We iterated over all valid times. We counted bits using bit_count. We formatted carefully. Big takeaway. Sometimes brute force is elegant. When the search space is small. This mindset wins interviews. If this helped you understand bit counting better, comment, binary watch mastered. And tell me, would you solve this using combinations instead? See you in the next problem.